Please meet Denis.
All right, hey, I'm Denis. I'm from Berlin in Germany. And you might know me from a handful of projects such as Nanoc, which is a static site generator that's been around for about 12 years. Cree is a tool for writing Ruby command line interfaces. ddmemoize is the best memorization library for Ruby. ddmetrics is some tool for adding telemetry to your applications, and a bunch of other things. But I wanted to talk a little bit about the company that I work for, which is Movinga. And Movinga is a moving company that aims to bring the moving industry into the 21st century. And so Movinga operates in Germany, France, and Sweden. So if you want to move house in any of these three countries, then Movinga is a good choice. So Movinga's mission is to provide removals at fair prices, and fair prices is key here. And so prices is what I want to talk about a little bit more in detail. So one of the things that I've worked on in the past at Movinga is the pricing algorithm. And given that the pricing system is so central to Movinga's mission, the pricing algorithm is pretty important. So as a disclaimer, I can't share the pricing algorithm that Movinga uses. That would be business secret. And when I talk about the pricing algorithm, I will use a simplified one. And so pricing algorithm is also probably a little bit dull, so I'm not really going to talk about the algorithm itself, but I'll talk about the technology behind it and also the human processes. So you might be thinking, why would we need a pricing algorithm in the first place? Well, there are a few different ways of calculating the price for a move. And the first one is having a fixed price, let's say 500 euros for every single move. But that would mean that if you move across the country from one mansion to another, then you would pay the same as if you were to move within the same city from one studio apartment to another studio apartment. So that's not fair. How about we calculate the pricing per hour? Well, now instead of trying to calculate the price, you now have the problem of calculating or predicting the number of hours that a move will take. And so that is also not really going to work. That's hard to calculate. We could also do the move and then wait and see what the price turns out to be. That is not really going to work because customers really like certainty. They want to know what the price is up front. And this approach is also very easy to abuse because moving companies could deliberately work very, very slowly and just sit and do nothing while the price for the customer goes up. So that is not great either. So that's pretty risky. So the fourth option is an algorithm, and this is the right choice. Yes, and so an algorithm will calculate or predict the price as accurately as possible. Now, a pricing algorithm takes a whole bunch of different parameters into account. Most importantly, the moving distance. So the longer the moving distance is, the more you'll pay. The number of items, and more specifically, the total space, the volume that all your items take up. Whether or not you have any special items, so if you have a piano, for example, that is more difficult to move, and that takes special care. Whether or not you have an elevator in your move out address or your move in address, and so on and so forth. So the way the current pricing calculation is done is determined by business people, and they work together with the business intelligence team to come up with proper pricing formulas. And those formulas are then handed over to the development team, and the development team will go to implement those formulas. And this works pretty well, but there are a couple of issues with this. So business people need to know, or often ask, why prices are the way they are. So sometimes there are prices that are very high or very low. And then business inquires like why that is. Now, there is a system for generating a breakdown for this price that exists, but it's not detailed. It's not very detailed, so the business people do need to get in touch with the development team. Issue number 2 is that developers need to be involved in the implementation of new pricing formulas. They get the formulas from the BI, from the business people, they go and implement them. And this can be slow because that work ends up on the team's backlog, where it needs to get planned in, and eventually it might take weeks before a change to the pricing system is rolled out. And business people can't really make those changes themselves because they can't code, and they also don't want to code, and then it also involves testing and deployment and so on. So that's not an option for them. Issue number 3 is that developers have no good way to verify whether a pricing implementation is correct. A price is a number, and the only real expectation of a price is that it's above 0. If it's below 0, then you would get paid to move, which I don't think is realistic. But you can't really write good test cases for prices. And number 4 is that it is difficult to dry run to test out new formulas. So there is a staging environment, but there still needs to be quite a bit of back and forth between developers and business people, so it can take quite a while before a change goes into production. And so at the moment, the BI team have their own copy of the database, and the BI team implement the formulas themselves to test things out, and then hand over that implementation or that formula to the development team that have to re-implement that in Ruby. Because BI people, I think they use Python. So that's not very efficient. Here is a very simplified example of a pricing formula. So in this case, the total price for a move would be 200, the base price plus the volume of items in cubic meters times the distance. This formula is fake because if you were to move a distance of 200 kilometers and your entire inventory is 20 cubic meters, then you would pay 4,200 euros according to this formula, and that is very high. This formula, this implementation also doesn't take the breakdown into account. So again, this is simplified. But I have a very different idea of how I want to implement pricing formulas. So if you look at this formula, you can see 4 different things. You can see a sum, you can see a product, you can see a variable, you can see 2 variables even, and there's a constant as well. In a real-world formula, there would be other types of things, for example, exponentiation and division and so on and so forth, but this is a simplified example. So I want to make those 4 types more explicit, and so I'll define classes for them. So I'll have a sum expression that has a left-hand side and a right-hand side. A product expression is very similar. It has a left-hand side and a right-hand side. There's a constant expression, which just has a value, and finally we have a variable expression with a name. And so now we can build our formula using these expressions. So our pricing formula is a new sum expression of a constant expression and a product expression of a new variable expression with the name volume and a variable expression with the name distance. This is exactly the same formula, it's just formulated in a different way. So we'll still need a way to evaluate this formula given some parameters. So if I have a hash of parameters, volume is 20 cubic meters, my distance is 200 kilometers, and I pass those parameters to an evaluate method on that formula, then I expect to get 4,200 out of it. So for each expression type, we will need to implement the evaluate method. So for a variable expression, what you do is you take so to evaluate the variable expression, we get the value from the parameters for the key that matches the name of the variable expression. So in Ruby, you can use .fetch, which will raise an exception if the key doesn't exist. So it's very similar to square brackets, and I prefer fetch because I like exceptions and I want my code to fail as early as possible. For a constant expression always evaluates to the same value, the value of the constant. For a sum expression, this is a bit more complicated. You evaluate the left-hand side, you evaluate the right-hand side, and then you sum the two together. For a product expression, it is very similar. You evaluate the left-hand side, you evaluate the right-hand side, and then multiply both. So now, if we have params, volume 20, distance 200, we pass that to evaluate, then we get the expected outcome, which is 4,200. So what have we achieved at this point? Well, at this point, we've achieved absolutely nothing, because instead of having a very simple way to calculate the price, we now have a very complicated way to build the price. So what is the point? Well, the point is that it makes some things quite a bit easier. For example, now it is much easier to automatically generate a breakdown. And a breakdown is a tree representation of an evaluated formula, where you can see the value at every single point within that formula. So for example, if I were to generate the breakdown for this formula, which is exactly what we had before, then we would see something like this. Here, this is not the nicest representation, but you can see that the volume evaluated to 20, the product evaluated to 4,000, and so on and so forth. For this breakdown, we'll need an entity that represents each node within this tree, and I'll create a class called node, which has 3 attributes. It has a name, which could be sum, or product, or const, or var. It has a value, which is what we were playing around with all along, and it also has children. For example, in this breakdown, the root node is a node with the name plus. It has 2 children. The value is 4,200, and it has 2 children, the const node and the product node. And similar for that volume bit in the breakdown, that is a new node with the name var volume. The value is 20, and it has no children. So the way we'll generate this breakdown is by letting the evaluate method return a node instance rather than a value. So this is what our variable expressions evaluate method returned before. But now, rather than letting it return a value, we'll return a new node with the name var and then the name of the variable. The value is exactly the same as before, and it has no children. For a constant expression, instead of returning just the value, we return a new node with the name const. The value is what we had before, and no children. For a sum expression, this becomes a bit more complicated. So we'll have to evaluate the left-hand side, we'll have to evaluate the right-hand side, and then we create a new node with the name plus. The value is the sum of the values of the 2 child nodes, and the 2 children nodes are left node and right node. We can do exactly the same for product, except that instead of adding, we now multiply. So now, the evaluate method and all these expressions don't just return the value, but they return the context of how that value came to be. We can implement to_s on node to return a representation. Unfortunately, I couldn't find a nice enough implementation of this to put on a slide, but maybe you can. And so when you evaluate an expression, a formula with some parameters, and then print it, you get something along these lines. You get the breakdown. If you don't care about the breakdown but would rather have just the value, then you can still call .value on that the node that is returned on the breakdown, and you get the value out of it, which is still 4,200. Now, the really interesting part about this implementation is that we managed to add breakdown generation, without changing the original formula. The original formula we left intact, and we just added something new on top of it, and that I find really, really interesting. So let's take a look at those 4 issues that I mentioned before. So one of the first issue that we had is that the business need to know why prices are the way they are. Now that is solved because we can generate a breakdown which business people can look at and understand. But the 3 remaining ones are still pending. That is because I still have some trick up my sleeve. So let's take a look at the point part 2, because I built a GUI to manage pricing formulas. So let's take a look at a demo. This is German for demo time, by the way. Let me see. Oh no. How does this work? Yeah. Wait. So I'm supposed to be able. No system updates. I prepared this so well, and it was going to go super smooth. Arrangement, mirror displays. So you can use Command F1 to enable mirroring, but I have this touch bar and then it doesn't work, so that's not so great. All right, so we're back to normal. What I have here is a list of moves. It's fake. You have a move ID, you have a volume, you have distance, then you have 2 pricing columns. At the moment, they are identical. If you scroll up, which you saw earlier, because I was being careless, you have a text field where you can enter a formula. So in here, I can start playing around with different versions of this formula. So I might say that like multiplying volume and distance doesn't make sense, so I can add them instead. I can click update, which will update the new price column, but leave the original price intact. And so I can keep playing with this. For example, I can say I care about, let's play around with volume times 10, and I can test this out whether this is a realistic formula, and so on and so forth. Something else that I can do is if I don't understand why a certain price is the way it is, then I can click on it and have a graphical representation of this breakdown. So this is very similar to the textual one, except that now it is built with SVG. I can keep playing around with this, and eventually I might say like, oh, I really like this pricing formula. That's the one that I want to use for the actual prices. And then I can click this commit button, which will now update the original price. So now the pricing of all our moves is different. And I can keep on going. So if I don't care about the base price, I can change this and divide the distance by 2, and so on and so forth. That is the UI for it. How do I... All right. This went so much smoother the last time. Oh well. So, one of the bits of this demo is that it took a string and then generated an expression, a formula out of it. And the technique used for taking a string and then turning it into something that the computer can understand is called parsing, and so we'll need a parse function. Now, as one of my hobby projects is to write a parser, so I wrote a parser, it's called dparse. I prefix everything with D because I really like my name. So this is a Ruby gem for writing your own parsers. It uses parser combinators. And I want to show you how you can use it. Now, I don't want you to think about how it's implemented, because it will look like magic. The implementation is nice, you can check it out, but I'll just use it to implement a parser for this particular language. So what I'll do is I'll create my grammar module, I'll extend it with dparse DSL, and then I'll define a digit as any character in the range from 0 to 9. A constant expression is a repetition of one or more digits, which I want to capture and then turn into a constant expression. The data is then, when I have the data, I call .2i with base 10, because these are base 10 numbers. The variable expression is a repetition of one or more characters in the range A to Z. I capture that as well and create a variable expression out of it. An operand is either a constant expression or a variable expression. Oh, sorry. And an operator is either the character plus or the character multiplication times. So I capture that as well. Then I define an operator sequence as being operands interspersed by operators, which I capture and turn into an operator sequence expression. Now, this operator sequence expression I haven't shown you before, but I will get back to it later. And finally, the root of my grammar is this whole operator sequence followed by the end of the file. And of this sequence of two things, I only care about the operator sequence expression. I don't care about the end of the file. So now I've defined my grammar. So let's take a look at the input that I have. This is exactly the same formula as I had before. I can apply the root of my grammar to this particular string, and I get a raw expression out of it. Now this raw expression will look something like this. This is an operator sequence expression, and it has an array in it with some things that we can recognize, such as the constant expression, the variable expression, and maybe some other things. But it doesn't have sum expressions yet, and it doesn't have product expressions. So we'll have to take this, apply operator precedences and associativity to it, and I won't show it in detail how you can do it. But basically, you'll have to take this operator sequence expression and turn it into sum expressions, product expression, and so on. And one technique that you can use for this is the shunting yard algorithm, which I've used in the past, and it works pretty well. So once you take that raw expression, you pass it to resolve operator sequence expressions, which will finally get rid of this operator sequence expression bits, and then you'll finally have the proper formula with variable expressions, constant expressions, sum expressions, and product expressions. So let's take a look at the input again. This is my string. I can finally apply the root of my grammar to that string, resolve all my operator sequence expressions, and then finally I get the actual pricing formula out of it. Once I have this pricing formula, what I can do is I have some parameters. I can call evaluate on that pricing formula that I parsed, pass the parameters to it, this will return a node in this breakdown tree. If I call value on it, it will return the actual value of my move or the price of this move, which in this case would be 4,200 as before. So let's take a look at the 4 items that I had on my list. So we already talked about business needing to know why prices are the way they are. We talked about this is solved. Let's take a look at developers need to be involved in the implementation of new formulas. This is no longer the case because we have a UI where other people can also play around with it. Developers have no good way to verify new formulas. I think this is not very relevant because developers are no longer involved. And I hope that the people that would use this kind of interface would know what they're doing. These would be the BI people. Lastly, it is difficult to dry run new formulas is a solved problem because now within this UI we can have 2 different prices and we can play around with them and finally say commit, which puts them live when we're happy with them. So we're done. We've finally implemented something that works. And that's fine, that's good, but I have some more ideas. The point of treating code as data is not just that you can automatically generate a breakdown or build a UI for it, but there's some more items. For example, we can implement versioning and locking. What I mean by versioning is that every single formula that you store in the database, or whenever you update the database, you update the pricing formula, you store all the old versions of the formula so you can take a look at what the old versions were. And by locking, I mean that when you're negotiating with a customer about a certain price, you don't really want that customer to suddenly be treated differently because there is a new version of this pricing formula. So while you're negotiating, the pricing formula for that customer is locked for that particular customer. So even if the pricing formula changes, for that customer, it will remain the same formula. That's number one. Now you might say, well, Ruby is slow, and now you've implemented a language on top of Ruby, which will make it even slower. If that's the case, then what you can do is you can take those expressions and then translate them to Ruby. And then you automatically have basically gained the performance benefit of having just normal Ruby code, and your performance loss might just go away. Now you might say, well, that's still not fast enough. Well, imagine that your system is backed by a database, a SQL database. What you can then do is you can take your expressions, translate them to SQL, and have the pricing calculation be done on the server. And this will be faster also because you eliminate any kind of network traffic from and to the database entirely because the calculation is done there. The data never leaves the database. You might say, well, we don't have a database and Ruby is still slow or whatever. What you can then do is, if you really want to, you can take this code and compile it to native machine code with LLVM. Now, I'm not saying that this is a good thing to do, but you have the option to do this. Now, these are all the benefits that I wanted to talk about. And one question that you might have on your mind is this over-engineering? And that's a very good question, and it's also a bit difficult to answer. The answer is that it depends. It depends on what your requirements are. If your requirements is that you need to have a breakdown that is always correct and completely and complete. If it needs to be executed fast, if you need a UI where everyone can enter their pricing formulas, then maybe this implementation is the simplest one that you can come up with. And in that case, is it over-engineering? Probably not. But again, it really depends on what your requirements are. And generally, my approach is to keep things as simple as possible. And sometimes the simple solution is still pretty complex and might involve LLVM. That is nearly all I have, but I do have some takeaways before I end. I have two takeaways. The first one is that it is much easier to reason about code, to reason about data, than it is to reason about code. Because you treat code as data, you can automatically generate breakdowns both textually and graphically. You can compile it to SQL, you can compile it to Ruby, compile it with LLVM, and so on and so forth. And that's because we've lifted an implementation in a general purpose, powerful language. We've taken it from there and created our own language, which is very limited in power on purpose. And that's exactly what made it possible to do this. The second takeaway is much more generic, which is try novel approaches. I started this just as an experiment, and I didn't know where it would take me, and I had no idea that I would come up with all of these things. But because I tried this approach and saw where I came up, I basically wouldn't have done any of this if I hadn't just continued on. Think outside the box. And with that, I will leave you. Thank you.
Yeah. Thank you, Denis. We may have time for a couple of questions.
Thanks for a nice presentation. The question is, have you shown this approach to your business people?
I have. So I used to be in a team that dealt with this. I'm not anymore. And I also think it needs quite a bit more fleshing out of what the requirements exactly are and how much we would benefit from it. But for the time being, there's no plans to actually use this.
Technically, the interesting part is why they don't use something simple like Excel.
So the actual implementation used to be in Excel, but it was horrendously complicated. And you basically need a dedicated system to deal with this.
One more question.
Speaking about, I'm here. Thank you for your talk. Speaking about your parser, have you considered Ruby standard library string scanner for it instead of rolling it from the ground, from the scratch?
Yes, but primarily I wanted to just play around with something, and I think that so in Ruby I have a whole bunch of parsing libraries. Some are fast, some are slow, some are weird, some are not weird. Ruby's standard library comes with a string scanner, which is quite interesting and useful, but I don't think it fits this particular purpose. Yep.
Okay, thank you very much.